Well, we're at the end. We're close to the end anyway. We do have the public forum tonight. Just for the record, I'm Les Johnson. I am the General Chairman of TVIW, and I'm also, in my day job, work for NASA. But I'm not here speaking for NASA, even though I'm going to be talking about technology work at NASA, a project I'm working on where all the information is publicly available, and a secret plot to have an interstellar voyage begun before the year 2020. So what I'll talk about and briefly review for those that may not be 100% familiar with solar sails, and if you unfortunately didn't take Space Propulsion 101 on Sunday, I'll bring you into the fold a little bit about solar sails, their history, and where we're going. Next chart. So just to remind you, a solar sail is propelled by reflecting sunlight, not the solar wind. Solar wind are solid particles. Sunlight is light. Light has no rest mass, but it does have momentum. What that means is when you go out on a sunny day and the sun is shining on you, it's pushing on you. It's maybe a few ounces per football field of area, of force, not much, but it's a very small push. And when you get into space, you have a continuous low thrust to give you acceleration, very easily thought of in F equal ma. You've got a constant force from the sun if you're at a certain distance. Spacecraft mass is m. To get a big A, you want a small mass because you have a constant force. So you want to make your spacecraft as small and as lightweight as possible. The sail materials are typically, in the near term, some kind of plastic, polyimide. This is a sample that I'll pass around of a material called CP1 with 100 nanometers of aluminum on it. This is the material that will be used for the first generation of solar sails. So I'll pass this around, and yes, you can tear it if you really work at it. If you just handle it, look at it, pass it around, you probably won't damage it. So let me go ahead and hand this out so folks can see what the material is like that we're talking about flying with a sail. And just to get us level set in terms of how you navigate with a solar sail, when you have a point source of light like the sun, I'm going to assume the sun is in the back of the room and it's shining up this way. Here's my sail. It's deployed outward, looks just like a sailing ship of yore. You would expect the light to reflect from it and push it radially out from the sun, which would be true if we were just to throw it out in space and it didn't have some kind of orbital velocity already with it, considering that the Earth is moving around the sun. So whatever we launch from the Earth is also going to be in orbit around the sun. And therefore, as it's flying radially outward, it's actually spiraling out. Well, if you tip and tilt your sail, you can change the angle that the light reflects from it, okay? And if you remember from first year physics, doing those horrible problems with the block on the inclined plane and having to find the normal force and the net force on the block, you know all about adding up forces and getting a net force. Well, if you tip or tilt the sail and change the angle that the light reflects from it, you can get a component in the force along your velocity vector to accelerate, or if you tip it the other way, you can reflect it so that you're decelerating. And that's what you need to do to change your orbital distance from the sun by changing your velocity at which you go around the sun. So a solar sail can actually work very well going toward the sun, and as you get closer to the sun, you get more light falling on the sail. As we've had our folks here talking about with laser sailing and very close solar approaches, and Sandy had wonderfully showing the inverse square law in his chart today. Get close to the sun, the thrust goes up dramatically. Get far away, it drops off. Well, we know this works, next chart, because as early as the 60s, and this is a chart borrowed from Sandy, who originated it in some early presentations, is NASA flew the Echo balloon, big silver balloon, flew in the upper atmosphere, aerodynamic drag started bringing it down. They had radar data of where it was, understanding its orbit, and they were actually able to take out of the aerodynamic drag that it experienced the solar pressure that was acting on the balloon. Turns out this is a well-known phenomenon. There are geocommunication satellites in Earth orbit that have big, huge solar arrays, and the sunlight pressure causes them to have to reorient themselves periodically because otherwise the spacecraft gets torqued off of its nominal attitude. All right, next chart. The modern flight of solar sails was really kicked off by the Russians. The Russians flew an experiment called Znamya. Now, Znamya was not ostensibly a solar sail project. Basically, what the Russians wanted to do is solve the seasonal affective disorder and alcoholism in Siberia. Turns out Siberia is cold and dark at night, especially in the winter where the nights are very long. So in order to improve productivity, reduce alcoholism, and increase morale of the Russian people, a group of scientists said, wouldn't it be great if we could reflect light from space to light up our Siberian cities at night and make people happy? Da, comrade, let's fly an experiment. So they did. As a spacecraft progress vehicle undocked from the not the International Space Station, the Mir space station, they deployed essentially a slowly spinning reflector, lightweight reflector, G. That's what a solar sail is, to demonstrate deployment. And there was actually light reflected to the ground, and it was observed on the ground as it rapidly tracked across the planet. There was a follow-on mission that they convinced their funding sponsors to do. And I would love to be in the bureaucratic meetings where you're trying to convince people this is a great thing to do, right? You know, they probably had charts of how many people would not become alcoholics and everything else. So they flew this, but they had an accident. The accident was an antenna didn't retract. They deployed the sail, it shredded. Okay? That was the end of the Xenon experiments. Now, I'm not going to go through the complete history of solar sails. I have a talk on that, and I could do that, but I'm going to give you some of the high points. Next chart. Another high point was the project that Sandy and I worked on at NASA, where we developed two very large solar sails. This is a little picture, but the diameter of this sail from here to here is 100 feet, 20 meters on a side, deployed in the world's largest vacuum chamber in Sandusky, Ohio. Now you know a bit of useless trivia. Where is the world's largest vacuum chamber? It's in Sandusky, Ohio, but it's awesome. It was pumped down to vacuum of space. This is where NASA tests its large space systems. The airbags for the Mars landers were tested here. All sorts of cool stuff has been tested there. And these sails, there were two different approaches, were deployed autonomously, both in ambient and then pump all the air out and tested there. We did thermal vac testing to make them cold. One of the approaches needed to be cold in order for the booms to rigidize. And all of these sails, which are 20 meters by 20 meters, 400 square meter sails, packaged into a box not much bigger than this podium. Okay, with 4 50-foot booms that came out of it. Pretty amazing. With the material you're holding that I'm passing around. That project, in typical NASA fashion, was canceled. Okay, right before we got to flight. And all the money went to the great effort of the Return to the Moon program. And you know where that went. So, well, it didn't get us back to the moon. It got canceled. So what happened, though, and this is to the credit of Sandy and the team, is that we had this material left over, was delivered to NASA by the contractor. So we had all this sail material. So they said, we've got all this sail material. We've got people who are funded because it's not the end of the fiscal year. So the funding is here for the people. We have a little bit of dollars. So the team decided to build a CubeSat-sized solar sail as a deployment demo. And that deployment demo, and I'm bringing up my timer so I don't run out of time, did a flight on a 3U CubeSat. Now what a CubeSat is, imagine a square block, 10 centimeters by 10 centimeters by 10 centimeters. We're defining units. That's 1U. That's a 1U CubeSat. There are small spacecraft that have been launched into space that are no bigger than that, all right? With the miniaturization of electronics and communication systems and ham radio receivers listening, universities all over the world are popping these CubeSats into low Earth orbit and unfortunately creating space junk, which is another topic. There are also 3U CubeSats, which are 3 of these things stacked together. And within a 3U CubeSat developed by the Ames Research Center and the Nanosail D, built by Marshall with these booms, this is 3.5 meters on a side, total of about 10 square meters, deployed from a CubeSat, flew successfully in space. Next chart. And you can see a picture of it here from a ground-based observation. So now this project, this Nanosail D, did not solar sail. It was a demonstration of deployment. There were no guidance, navigation, and control systems on board. There was no way to orient it to get it to sail. And it photon sail, it sailed in the upper atmosphere because it was in fairly low orbit. So it stayed in space, eventually deorbited and burned up, but it demonstrated an autonomous deployment from a CubeSat of a small solar sail. That's an important point. Next chart. Well, while we were canceling our solar sail program and building Nanosail D, The Japanese picked up basically after we canceled the big program, and they went and they flew Icarus, interplanetary kite craft accelerated by radiation of the sun. And I don't know why everybody keeps calling their interstellar stuff Icarus, because you know what happened to Icarus, okay? So you guys have just got to stop that, okay? But the Japanese were very successful. Their Icarus did fly closer to the sun. They were on a secondary payload that was going toward Venus. They deployed 14 meter by 14 meter solar sail, slowly spinning for attitude control, deployed beautifully. There is a series of pictures that it took of itself. These are actual photographs in deep space. These are the first solar sail selfies. And how these were taken is there was a little subspace craft with a camera, a shortwave radio transmitter, kicked it out because they wanted to know the state of health of their sail. Did we deploy? What does it look like? So they took a self-picture. There it is. Well, this was a kick in the pants. This was a challenge. The gauntlet was laid down. Japan did it. All right? Next chart. So, at about the same time, and if you work for an organization like NASA and you want to do science missions, you have to have scientists saying, we want the technology that you're trying to sell. It's a lot easier to get funded if somebody is saying, I want what you have to sell. Okay? Well, it turns out in a division of NASA, the Solar and Heliophysics division, they have done their assessment of what science missions need to be done over the next 10 to 20 years in something called the Decadal Survey. They do this every about 7 to 8 years. It's not quite on the decade. And they update it, but it is chock full of missions that can't be done any other way except the continuous low thrust of a solar sail. So what the solar sail community within NASA has been looking for a long time happened. We have scientists standing up saying, we need your technology. And at the same time, we have some scrappy technologists like Sandy and the team who worked on Nanosail D demonstrating it. And in the tradition of space race, we have a foreign country doing it. Okay? So you put all that together, and it's kind of a magic sauce globally for solar sail technology to develop. Now, I'll tell you that almost everybody working in the field of solar sails who gather every 3 years at the International Solar Sail Symposium, they're all us. They're selling solar sails for the near-term interplanetary capability, but almost to a person, they want to see sails take us to the stars, and they're sort of, selling themselves to do it in the solar system because that's a necessary step to learn how to make them go to the stars. And I can say that that's the majority of the sail community is motivated by our motives. And they're doing this near-term stuff because it's cool and it's the only way you can do it. And oh, by the way, we'll never convince anybody to let us build a big one unless we do the small ones first. So we've got mission pull. Next chart. So there's a lot going on today. I'm going to talk about Sunjammer, which was unfortunately canceled. Right? You hear that word before, right? There are 2 projects that are funded, one of which I'm the principal investigator for, which is the NearEarth Asteroid Scout. It has a sister mission called Lunar Flashlight, which I'll talk about. The Planetary Society has recovered from the Cosmos issues where the launch vehicle failed, no problem with the sail. They have their first Earth orbital solar sail that will fly next spring, LightSail A. It is a 3U CubeSat-based 32 square meter solar sail, and they're going to fly LightSail B a year after that. They're actually offering to do on-orbit operations to help us learn from what they do in our design of the project I'm going to tell you about. At the University of Surrey in the UK, located outside of London, they have 3 CubeSat solar sails they're developing, and I'm personally involved in one called Inflate Sail, which is going to be a 3U CubeSat solar sail, but instead of rigid booms, it's going to use inflatable booms. Inflatable booms are nice because they're lightweight. They use a gas to inflate, and they can have a material when it gets cold that it becomes rigid so the gas can leak away. It makes a very lightweight system. Remember, sail systems have to be lightweight, small spacecraft. You want the mass as low as possible. And not to be left out in the race between the US and Japan to keep building sails, the European Space Agency, which is a separate funding organization from the European Union, who funded these solar sails. Did you know Europe has at least two international space agencies? My colleagues here who hail from close to the continent need to explain to me how you can have 2 continent-wide space agencies. I'm not even counting the national space agencies, just 2 continent-wide space agencies. But they're doing that, and these are Gossamer 1, 2, and there will be a Gossamer 3, which will be about the same scale as bigger than Icarus and larger sail. So, next chart. Sunjammer, everybody's going to ask me about it, so I'll tell you what happened. At a very high level, NASA selected this project to demonstrate a very large solar sail, building on the work that Sandy and the In-Space Propulsion team did up at the Plumbrook tests. This 100-foot diameter solar sail with inflatable booms was selected to go to flight and was supposed to fly in 2015 to demonstrate a very large solar sail on the order of almost 40 meters by 40 meters. It was going to be pretty big. And for largely cost and programmatic issues and some technical issues, this project, next chart, was canceled, as in a couple of months ago. And we didn't have a whole lot of involvement in that. I had no personal involvement in Sunjammer other than rooting for them, because this is what's going to be necessary to enable some of the big missions. But in parallel with their effort, I was working with a team and selling what I'll now tell you about. Next chart. Well, let's skip through Light Sail A. This is a picture of what the Planetary Society solar sail looks like. Keep going. This is artist concept of the Gossamer missions that the Europeans are going to fly. They're going to start out with a 25 square meter CubeSat sail. Sounds familiar, coming from 3U CubeSat. And then they're going to get up to a very large sail, 50 meters by 50 meters, all using these rollable composite booms, very lightweight composite material for your booms. So they're making a lot of progress doing a parallel approach to what we're doing. Next chart. And this is a picture of the work at University of Surrey. That's the principal investigator, Vios Lapis. And they're going to fly their sails in about a 700-kilometer altitude orbit, where it will be able to measure solar photon pressure. Next chart. Now, the project for which this model is sitting here is something called NearEarth Asteroid Scout. Next chart. Nia Scale is, as it sounds like, it's going to go to a near-Earth asteroid. This is the actual size of the flight unit. It's a 6U CubeSat. It will be, at the time it flies, the second interplanetary CubeSat, at least that we're aware of. The first one is going to fly this year. It's a smaller CubeSat from JPL. This is a partnership between NASA Marshall and the Jet Propulsion Laboratory. JPL is good at building deep space spacecraft. Well, they're building the spacecraft bus. We at Marshall are providing the solar sail. The sail will be 85 square meters, about the size of the floor area of this room, deployed from this sail. On this spool, we have wrapped, folded, and spooled half of that solar sail. So there's over 40 square meters on this spool of the material that we handed around. It will fit here. The booms will deploy from underneath. The booms are 7 meters long, so there'll be 4 7-meter booms that will deploy outward and unfold the sail from the Nia Scale. Our goal is to go and demonstrate a capability to image, take pictures of, do a little bit of spectroscopy, and characterize some near-Earth asteroids. And we're funded by NASA's Human Exploration Office, because they need to understand what these NIAs look like before you risk sending people there. Next chart. Now, the target, 1991 VG. What do we know about it? Not much. It's a radar return. We know it's there. We know it's one of thousands of near-Earth asteroids that are being discovered, as their name implies, in near-Earth orbits, okay? It's not terribly large, 4 and 17 meters. Some of the questions we have about it: is it a single rock or a gravitationally loosely bound bundle of small rocks? We don't know. Does it have dust around it? Probably not. Solar photon pressure over millions of years probably would take this dust, put it in a different orbit, leaving whatever the bigger chunks are there gravitationally bound together. We do not know what it is. It's unlikely to have a companion. It's probably not 2 small ones. If it's more than one, it's probably a bunch of them. And we know its general rotational period based on radar observations. So we don't know a whole lot about it. Next chart. So we're going to go take observations. Nia Scale will fly for about 2 years. We're supposed to launch in 2017. We'll go to the moon, do a gravity assist around the moon, and then we'll be cruising for about 2 years. And we are going to match velocity with the Nia using the solar sail and fly by it at about 1 to 2 meters per second. So this is not a fast flyby. We're going to go and we're going to fly along this puppy. Now, as we do our imaging and we take pictures, if there's something we miss, we are a propellantless propulsion system. We loop out and we come back. Okay? Try doing that with a rocket. All right? Can't do it. Next chart. What does it look like? This is kind of what the systems are. We're using a lot of JPL spacecraft components that will be uniquely designed for this. CubeSat solar sail, CubeSat subsystems that fly on the University CubeSats in Earth orbit generally won't work here. We're not inside the Earth's protective magnetosphere. We're out in deep space. We've got a radiation environment that we have to deal with there that we don't have to deal with here on the Earth. So we got to have some rad, not hard, rad tolerant components, because rad hard will blow our budget. All right? Our goal here with this mission, this whole thing weighs about 10 to 12 kilograms, all right, is going to cost under $20 million and is going to return about 50% the science of a mission that costs about $400 million, all right, if we're successful. This is a high-risk project. Where's Donna? Donna, we do not have redundancy, okay? I'm sorry. We are not being redundant. We can't afford redundancy. This is a demonstration of a low-cost capability, all right? And we're building 2 flight units, and the second flight unit with a different instrument is going to be called Lunar Flashlight. Next chart. Well, let me give you an idea of the size comparison. Here's a school bus, here's this room, here's our sail, and again, this spool is half of the total sail dimension. By the way, there's the CubeSat from which it deploys, down in the bottom right-hand corner. There I am, the dark silhouetted puppet master of TVIW, and here is a school bus. Next chart. Keep going. I was going to show an animation, but I'm not. Now, let me tell you, go back one chart. I want to tell you about Lunar Flashlight real quick, and then I'll talk to you about the secret plans to turn this into an interstellar mission that I'm now making public by having been recorded. There is a sister mission that was proposed at the same time by JPL. It's called Lunar Flashlight. Those of you who are interested in putting a colony on the moon, you know who you are, all right? One of the key locations for doing that, so you can always have power, is the lunar south pole. Because the moon, unlike the Earth, is not tilted a lot. There's a little bit, but it's essentially the south pole stays in near continuous sunlight. There's also another neat feature at the lunar south pole. There are lots of craters that have been in darkness for 1 billion years. Okay? Now, why is that interesting? Well, that's interesting because the moon shares the same impact history as the Earth, going a long way back. Look at the craters on the moon. Not all of those are caused by asteroids. Some of those are caused by comets. What are comets? Comets are made of water ice. The Earth, we know, is pelted by comets. That's where a lot of our water came from. The moon was pelted by comets. But ice won't last long when it's 100 degrees centigrade in the sun, or 200 degrees on the surface of the moon. When it's in the sun, that water goes away. But what about the comets that might have impacted and gone in those big craters at the South Pole? Statistically, there's a high probability that there is still ice from a comet impact down in those craters at the South Pole. So Lunar Flashlight is going to use the solar sail to launch, same launch vehicle that we're flying on, 2017. They go to the moon, they capture at the moon, and they get their orbit such that at perilune, it's the periapsis, the closest point of their orbit around the moon, will occur over the South Pole within 20 kilometers of the surface, and they will tilt their sail, not to propel, but to reflect light into the crater, and then take pictures and look for ice. Because if there's water down there, it's a lot more likely that we can put a human base there and have cut that another element of the supply chain from Earth. So that's Lunar Flashlight, hence its name. It will be the identical spacecraft bus with a different instrument, the same solar sail. All right? So we're going to fly on the same launch vehicle, 2 different missions, 2 two-year missions, and they're going to do that. So what is this Interstellar Sail by 2020 business? Well, my co-author, Greg Matloff, who many of you know, is going to the next chart, is a big advocate of interstellar sailing. And I said, Greg, you know, this little CubeSat at the end of its life, whatever that may be, if we don't go to another Nia, that's to be determined, because, you know, we're a propellantless system. After we visit one Nia, depending on where it is in the sky, we could go somewhere else, right? As long as we stay within about 1 AU of the Earth, we can communicate with it. But I asked the question, could we put this on some kind of a trajectory that we get it going, and then when it dies or we can't communicate with it anymore, that it'll be on some kind of a flyby trajectory near the sun to give it enough escape velocity to leave the solar system. He did some preliminary calculations looking about the thermal characteristics of the sail material, looked at some of the orbital mechanics and said, yeah, Les, we can do that. You can get down to about 1/4 of an AU, And I think we can get a trajectory that if you drop it into that, even if the spacecraft dies, it should get enough from it, the flyby, to get a solar system escape velocity. So what I've talked to the project manager about, and not necessarily with the Interstellar mission in mind, but just for an esprit de corps for the team, is while I still have some, collect hair samples from all the team members, put it in a little container on the spacecraft. At the end of mission, we're going to dive into the sun, and we're going to send a piece of ourselves to the stars. Okay? So that's the esprit de corps builder for our team. This interstellar leg of the mission is not yet approved. Camera, not yet approved. It is something we're going to propose that if we're fully functional, we've done our primary mission, everybody's happy, our sponsor is drinking champagne and saying it was a success, what do we do now? I want to raise my hand and say, I've got an idea. So, with that, I will stop and take questions.
Using a little bit of advanced knowledge here. And how, pray tell, is this wonderful little, or both of these wonderful little cubes going to be launched?
Oh, well, right now we're manifested to fly on the first full-up test flight of the Space Launch System, the SLS. And we would be kicked off of the SLS after the Orion is kicked off to go to the moon. And there are going to be at least 10 CubeSats, 10 6U CubeSats that are going to be in the MSA, which is the big adapter. And those will all be kicked off one after the next. NASA has a call on the street right now for additional payloads for rides. So if people have their own CubeSats that are interplanetary 6U CubeSats, just happen to be in development or in the waiting in the wings, and you don't need NASA to pay for it, you can be considered for additional launch on this launch option. So that's coming up out there. We're also looking at additional options for launch because, quite frankly, the most expensive part of developing a space system is the upfront engineering. The recurring cost for this is cheap. If someone were to come to us and say we want a third unit, the cost for that unit will be a fraction, like 25% of what the development cost for the whole thing has been. So if you want to go fly Sail and you want to do something with it, it's something that we should be talking now because we're laying those long-range plans for things now. So, yeah, Jim?
Les, when it kicks off the SLS, at what altitude would it be?
Well, it'll be on its way to the moon. I'm not sure exactly how far out we're going to be. I'd have to look at the trajectory.
The flashlight, how long will it take to get to the moon? How many passes over the sail do you anticipate, over the South Pole do you anticipate?
Okay, the Lunar Flashlight will get to the moon fairly quickly, like within a few days. But the problem is it won't be in the right orbit. And that's where the Sail propulsion system will take about a year to a year and a half. Remember, it's low thrust.
Yeah.
To slowly get it into that polar orbit and to crank down, crank down the periapsis so that they can get in the orbit they want to look in the crater.
And what altitude, you go down to 20 kilometers, how many orbits do you anticipate making?
Oh my gosh, I have no idea. It's a lot. I can look that up for you, but I don't know.
Does the orbit precess enough to carry you away from the original place, locations on the pole?
It does.
Yeah.
It does. And we have to manage that as we thrust. That's exactly right. That's part of the whole attitude control and navigation problem. That's right.
Okay.
Yeah, that's correct. We've got a question back there and then up here, and I think we've got time, and then I have one other statement.
Thanks, Les. It's so exciting. Tell me, the management problem, is it significant? Or could we actually have 50 or 100 of these doing different scientific ventures simultaneously under software control?
Well, the management of the flight, you mean?
The management of the craft in flight and as it's navigating to final position and final mission.
That is, we're going to be learning as we fly. No one really has a lot of experience navigating in real time a solar sail in deep space except the Japanese, right? And so we're looking at how to make this as autonomous as possible, knowing full well that for the first few months, it's not going to behave exactly as we predicted in our models, because we will have to have gotten the center of mass exactly right, the center of pressure exactly right. Is the sail completely in plane or a little bit off will all affect the thrust vector. So the first 2 months of flight are going to be, how do you fly this thing anyway?
It's just
all right?
the drum control.
It's trimming it out. After we get to the point where it's fairly predictable, the benefit we have is it's low thrust. Everything happens slowly. Okay? So if you mess up a command, you're not likely to kill the system. It's going to take a while to react to it. You say, oh my gosh, we shouldn't have done that. You can undo it pretty easily. Solar sail systems for interplanetary flight are fairly forgiving in terms of command and control. So I'll be able to better answer that question as we understand it better. I don't know right now. I don't know. One question, and then I have a closing comment. Yeah.
Les, you said that you could mass produce these things. Have you designed them with that in mind?
We are buying as many parts that can be multiple fabricated as we can. Now, that doesn't mean there's nothing unique for this, because interplanetary CubeSats are not common, but the capability that JPL is trying to build into the bus for this mission, they want to use to go sell other missions.
Yeah.
And so the mass production of the piece parts and the components is in the plan. And we're building the sail at Marshall, but our plan is to have a commercial partner licensed to go out and build the sails. So we don't want to get in the business of selling these things. We're prototyping to develop and then give industry the opportunity to go flying. So my last comment before I give the closing workshop comments are, this is not a shameless shill. This is actually a meaningful shill. I co-authored a book with Giovanni Volpetti, and if you're in the solar sail community, you know Giovanni. He is one of the European experts on sail trajectories, and really, really smart guy. And Greg Matloff. We wrote this book about solar sails. It's a popular science book. First 2/3 of the book are not for the mathematically inclined folks. It's for interested lay people. Hey, what can a sail do? What kind of missions can it do? If you're so inclined, the last third of the book gives you the fundamental mathematics of how to work out how big to make a sail, how to navigate with a sail, and some of the trajectory work. So I've got copies of this for sale. It's $25 if anybody's interested. I've got about 5 copies left. And it also, if you were in my class on Propulsion 101, you received a copy of the book that Greg and I wrote called Living Off the Land in Space, which has chapters on a lot of different in-space propulsion systems in it. I was asked to let people know by somebody who was in the class that I have about 2 copies of this if anybody's interested in buying a copy of the textbook, essentially, that we used in the class. I have that available. And with that, I will close my Interstellar Sail moment and launch into closing the workshop. I am amazed I was able to do that. You all worn me out. I want to thank everybody. Everybody who's still here, all the people who came, all the people who presented papers, the people who were the runners that made it happen. I want to thank again the committee. I want to thank our sponsors. You all really made this happen. The Tennessee Valley Interstellar Workshop does not have aspirations for being the World Interstellar Space Organization. We want to make a contribution to whatever that is. We want to capitalize on the talent that's in the southeastern United States, leveraging expertise and subject matter experts from all over the world to do our part to us becoming someday that interstellar civilization. And what we've done here today with original papers, summary papers, hopefully out of the workshop sessions, and I think I saw some good stuff come out of the workshop sessions, and perhaps one of the most important things at a technical conference doesn't even happen in this room. It's the connections you all made in the hallway when we let you have time, and such. And I'm hoping that if you made such connections, please let us know, because it's important for us to know that we're doing something productive and helping move things forward. So I just want to thank everybody who's here. I want to thank everybody who worked on this, and it's been a tremendous workshop. Now, John, raising your hand. Yes.
Yeah, I wanted to reiterate the survey.
Oh, yes. We do. What's the second survey?
The second survey has a logo on it, and that applies to the track that you were in. So you judge the track that you participated in. The survey without a logo is the whole shebang.
So do both.
Do both surveys. We really need to hear from you. I'm going to reiterate something I mentioned earlier. We are actively seeking additional support. We have some new projects that actually emerged during this workshop that we're going to put the meat on the bones for and announce soon, that have come out of this particular workshop for TVIW, and we will be making that known soon. So it's been productive for us, hopefully as well for you. And we are seeking people who want to contribute and be a part of our organization. If you'd like to volunteer, The pay is awesome. The payoff, I should say, is awesome. It's going to enable us to be an interstellar civilization someday. But it is an all-volunteer organization. And so if you're interested in being a part of that, at whatever level you can contribute, we'd love to have you. And we'd also appreciate you spreading the word to let people know we exist.